Welcome to Build Your Own CPU Part 4. In this episode, we'll be looking at the instruction byte, the addressing modes, and the microcode that operates the instructions. Now, to understand how the microcode works, you need to understand the T states. Now, a lot of CPUs would have a ring counter, and as the clock clocks along, it would cause a pulse to move along the different outputs. So on the first clock pulse, T0 will come on. On the second clock pulse, T1 would come on. Third clock pulse, be T2. Fourth clock pulse, be T3. And on this CPU, that would go all the way through to T15 before cycling back round to T0 again. So you would have 16 clock pulses for the 16 steps. Now, if we look at actual instruction byte, the top nibble to the left is the command. So there's a possible 16 different commands. On this CPU, we actually use 14 of them. You can make a CPU with a lot less commands than that, or many CPUs have many more commands. But on this one, I just picked 16 was enough for what I wanted to do. Now, the next two bits 2 and 3, they indicate where the source of the data is coming from. So if you're going to do like a move instruction, you need to know what to move. So source 1 could be, if you look on the left, memory direct. That means the next byte in memory holds the address of where the data is. So you'd move that byte into the memory register to actually collect the data byte. Or you could have register direct R1, which means you just get the data out of R1. And then there's register direct R2, which is just get the data out of R2. And then there's immediate mode. That means the data is embedded in the program and it's actually the next byte. Now, if you're doing a move, you need to know where to go. So bits 0 and 1 are the destination. You've got memory direct, which could mean the following byte holds the address, but if the following byte had already been used in source 1, it will be the byte afterwards. You'll see as we go through the steps how it knows which byte to take. Then we've got register direct R1, so the destination could be R1, so it could be move a number into R1 or R2. There's no immediate on the destination because you don't want to move into the next byte on the in the program because you'll be overwriting your program. Now, some instructions like add need two sources. You're adding two numbers together. So source 1 is your first number, source 2 is your second number. But the bits 0 and 1 for source 2 also say that's where the destination is going to be. So if you want to add a number to R2, you do add immediate, the actual number, and that goes to R2, and it'll get written. We'll take the value from the byte afterwards plus the value of R2, add them together, and then save them back into R2. If that makes sense. Right. Now, if we actually look at that instruction, well, there we go. Add R1 to R2. So this will be a 1 byte instruction. So we take the values R1, add it to R2, and then move it to R2. So source 1 will be 0, 1, and source 2, which will also be the destination, is R2, which would be 1, 0. So here's your actual byte. The add command is 0010, so that's a 2 in the top nibble. And you've got 0, 1 here for your source, R1. And you've got 1, 0, the second source and destination of R2. So adding all those bits together, you get 26 in hexadecimal or 38 in decimal. So here is the actual microcode. Now across the top, that's all the control signals, the control bus at the top. There's 32 signals there. And here, down the left-hand side, are all the T states. T0, T1, T2. So they're the 16 steps you can go through to make the instruction work. And on this one, you see there's a lot of blank spaces, but that will come clearer later as to why there's blank spaces at this point. It's all to do with the addressing modes. So we start with T0. T0 and T1 are exactly the same for every instruction. So when you very first start, your instruction register will have a 0 in it, and your T state will be 0. Seeing as every instruction is the same, it doesn't matter what instruction the instruction register thinks is coming through. In fact, it doesn't even look at them, it just looks at T0. If T0 is on, it will put A input enable, that's register A input enable will come on. Program counter output enable will come on. And memory address register input enable will come on. So if we look at that, there's the diagram of how the CPU is put together. And we actually get these signals on. This is T0. So the instruction decoder comes up here, your control bus. Feeds down here. So to turn your A register on, your program counter in the middle here feeds up onto the data bus and goes into the A register. It also feeds down into the memory address register. And that's just it for T0. Then you get the pulse signal, which will lock those values into the memory address register and the A register. And the pulse turns off, clock turns off, T0 disappears. So now, the next thing to happen is T1 will come on. When that comes on, the adder output enable will come on. The program counter input enable will come on. The C register set will come on. Actually, the C register will be set to 1. The instruction register input enable will come on. So we're trying, this is actual read instruction to read. This is the fetch instruction, as is often called. Fetch instruction from memory. So it's going to go into the instruction register. Your memory chip select comes on to say we're reading in from memory, and it's a read, not a write. And B clear is set the B register to 0. So we've got 0 in the B register, we've got 1 in the C register, and we've got the previous program counter is sitting in the A register ready to go. So when T1 happens, it says add the A register. The B control register will set a 0 for the B here. So what's actually in the B register is irrelevant. So you've got 0 here, got 1 there, and the C register, which comes across from the status flag, comes along this dotted line and down into the adder. So you've got A, B and C all added together. So we've got whatever the program counter was, you add 1 to it and load it back into the program counter. That is how we increment the program counter. You notice we don't go into the memory address this time. But what is happening on the this cycle is the memory address register output address, that's on all the time. But now we've got the memory chip select is on and read, so we've got data coming up the external bus. It's isolated from the internal data bus. This is the external data bus. And that feeds across into the instruction register and gets latched in there on the pulse. So we've just fetched the instruction into there. So whatever the memory was pointing at, we fetched that instruction. And we've also incremented the program counter. So we've done 2 things at once on T1. Now, because we're using OX register R1 for the source, T2, T3, T4 and T5 don't actually have to do anything. But you will get a pulse, so you will get the pulse coming, so it will take 4 more steps to get to T6. Now T6 is all about loading the first bit of data, the first source. So in this case, we're going to get here, register 1 output enable. It's going to feed out from register 1 and it's going to put it into the B register. T6 is all about loading the B register. So if we look at that one, control signals come down. And here, so R1 data comes out onto the data bus, across and into the B register. And when the pulse happens, R1 gets latched into the B register. Now next is T7, which is nothing in that at all. In fact, the motherboard doesn't even do a T7, it skips it. T8, T9, T10 and T11 are all to do with the other addressing modes, so these ones won't do anything in this instruction. T12 is load register 2, so register 2 output enable will come on, and that will feed across into the A register. So T12 is all about loading the A register. And if we look at that, T2 comes out across and into A, and all the control signals tell it to do that. So again, when we get the pulse, it's locked into the A register. Now T13 is another one of those states we don't need. We only need 13 of them, so that one actually gets skipped. T14, this is where all the action happens on T14. This is different for absolutely every instruction. There's 99 variations. So what we're going to do here is we're going to have the adder output enable, because we're adding A and B together. We're telling the adder to do an add, that's this adder line here, rather than like the sub, it's adding. And then R2 input enable, remember we're going to put the second source was R2, is also the destination, so we're going to put the destination into R2. Now we want to know if there's going to be a 0 or not, so the 0 input enable is on. The carry input enable is on, even though I've misspelled it. And the C register is cleared, because this is just a straight add without adding carry or anything, so you've got to make sure the C register is clear. So we've got A going into the adder, we've got B going into the adder, the C register has been set to 0. Coming across, we have A plus B plus C, so effectively we'll get just A plus B, and that will feed out into the R2 register. And the status register's got an input, because that's the 0 and carry coming to the status register. And that's the end of T14. So that is the whole command. Now let's look at the immediate addressing mode, which will be add the immediate value to R1. So a number, 0 to 255, plus R1 is saved into R1. So we've got the same instruction for add, 0010. Our source is now 11, which means immediate, and our destination is R2, 10. Which is add all the bits up. We've got hex 2D, or number 45 in decimal, would be the byte. So what we're going to do here, see, this one's a little bit more complicated. T0 and T1 are exactly the same as before. So that's T1. Load your program counter into register A and the memory address register. And on T2, increment A and put it back into the program counter, and grab your byte into the instruction decoder to see what instruction it is. So now we're going on to T2. Now we're a little bit different here. You notice there's stuff in there. What we've got to do now is the program counter always points to the next byte to be read. So you read the byte, then increment it. So T2 and T3 are very similar to T0 and T1. So we're going to load the program counter into the A register. Yeah, program counter out into A. Going to also load the memory address register. That says in set the address lines. Have a look at that. It looks very similar. Program counter comes out into A, and it also goes into the memory address register because we want to grab that byte. We go back here, look at T3. T3 is slightly different from T1. You're going to have the address output enable, program counter input enable, and the C register at 1, B register would be 0. So there's memory access on T1, but it's not on T3, because all this is doing is incrementing the program counter. That's all that T3 does. So T3, we've got the program counter was in A, B's at 0, C's at 1, so it adds 1 to A and puts it back into the program counter. So the program counter has been incremented to look at the next byte. Although the memory address register has got the current byte address sitting in it. So we're not using 4 and 5. We come back to 6 again, where it's load the B register. In this case, it's from the data bus, coming out from the external data. So we need the memory chip on and the read to say you read in memory, and you've got to turn the data bus buffer on to say read the data in. So the address is already set there, the data comes in, and this time because the data bus buffer's turned on, data comes straight in, up onto the data bus, and then gets read into register B. So now 7 doesn't do anything. Because we're on R1 now, we don't need 8, 9, 10 or 11. We go straight to 12, which is R1 out into the A register. So we move R1 into the A register. So the B register is containing the byte, the next byte in memory, and the A register is containing whatever in R1. Then we come down to 14, where the action is again. Add her out, and it's an add. R1 input enable, because we're going back into R1. We want to check for 0 and carry, set those flags as necessary. And the C register has to be cleared, because we're just doing ordinary add without carry. So we add those together and feed it back out into R1 and status register. Next we have the memory direct addressing mode. Here the following 2 bytes hold the addresses of where the data is we want to add together and where to put it. So the add command will be the first byte, the next byte will be the first memory address, and the next byte will be the next memory address. So we'll add the first memory address to the second memory address and save it back to the second memory address. So here's the command. We've got the same add command, but now we've got addressing mode 0 for the source and addressing mode 0 for the second source and destination. So the actual byte will be a hex in 20 or the number 32 in decimal. So T0 and T1 are exactly the same as before. Get the instruction and increment the program counter to look at the next byte. So usual program counter out into the adder and memory address register, and then increment the program counter. So the memory address register is looking at the instruction and has loaded it into the instruction register. Next, with T2 and 3, we need to get the next byte in memory. So again, we're going to load the memory address register with the program counter, increment the program counter, and save it back again. So T2 is program counter into the A register and the memory address register. So we're now looking at the next byte after the command. T3 will then increment it and save it back. So increment and save back in the program counter. So the program counter is now pointing at the next instruction, while the memory address register is looking at the current byte we're working on. Now we come to T4 and T5. Now we have to load the data we just loaded in from the byte after the instruction, because that's the address, and we've got to put that address into the memory address register to point at the actual piece of data. So we're going to get the data in by the data input enable and save it into the A register. So we've got memory chip select and read on, so we're reading memory coming through the data bus buffer into A. So the data, because the memory address is already set up, the data's coming in and into register A. T5 has got to load A into the memory address register to point at the actual piece of data. So we just take register A, can actually come out onto the data bus as well. The original drawing's got an arrow missing, so I'll put a new one here. B register can come out as well. Come across here, down into the memory address register. So we're now looking at the actual data. And T6 is load the B register with the actual data. So we're coming in, doing a read on memory chip select, data bus buffer input into the B register. So the address is still set, data comes in, cross onto data bus and into the B register. So the first source always goes into the B register. Now you may notice that 8, 9, 10, 11 are the same as 2, 3, 4 and 5. In fact, the instruction decoder cards are physically the same. They just have different T numbers coming. That one's got T2, T3, T4, T5 going into it, and the duplicate card has 8, 9 and 10 or 11 going into it. So 8 is get the address, the next byte into there, increment your program counter, then read the address in, load it back out to the memory address register. So your memory address is now pointing at the actual piece of data. So 12 is load the A register from memory. There's your memory select lines coming in through your data bus buffer into register A. So you're getting your second piece of data from the second address into register A. So B has got the first bit of data in it, A has got the second bit of data in it. And then we come to step 14, T14, which is add them together without carry, and so you've got data out, it's got to go back out to the memory. So we've got memory chip select, so we're going out to memory. The read is off because it's a write. C is clear because we're not adding with carry. But we are checking the carry and 0 for overflows and 0. And we've got data bus buffer is on, pointing outwards. So the data is going to be added up, go out through the data bus buffer into the memory. So there we go, add A and B together, and C, which is a 0, and the data comes out of the bus through the data bus buffer and down into memory. So we've also got register indirect addressing mode. Well, we haven't got it. We should have had it. I was a fool when I was making this system. And what I could have done is just done away with R2, because you can just use a memory location. R1 and R2 is just a quick way of accessing memory and actually makes the program a bit shorter because you've only got a 1 byte instruction rather than multiple byte instructions. So what you would have had is R1 would have held the address of where the data is. Now I haven't got enough bits to implement this now. It's quite easy to implement. All you have to do is move the value of R1 into the memory address register, and there you have it. So I should have implemented that. It makes programming a lot smaller, but I didn't. So that will be in the next CPU. Now, in the previous video, you heard me talking about this skip if 0 command or skip if carry. They both work the same way, they just use a different flag out the status register. Now, the skip command is 1101, or skip if 0 is, but the source can't be 0, and the second source or destination can't be 0, because the instruction decoder will think this is a memory direct address for the source, but there's no source for this. So to make sure that T2, 3, 4, 5, 8, 9, 10 and 11 don't actually do anything, we make this an R1. You could have made it an R2, but I decided R1. An R1 for the second source. So that's all those bits for the instruction, which is hexadecimal D5 or 213 in decimal. Now see, we will look at a bit of pretend code here to try and explain how it's working. So when we come to this bit of code, the program counter happens to be at 10. And at 10 we've got subtract 1 from R2. Sorry, subtract 1 from R1 even. Imagine R1 has got the number 2 in it. So we'll be subtracting 1 from 2, and that's going to leave us with a 1 in now. But as we load the instruction in, which will be 3D and then the actual number 01 into the CPU, the program counter would have been incremented once from the instruction and again from the data, so the program counter would now be holding 12, which is the address of the next instruction. So sub1 from R2 actually happens on T14. The CPU clocks round to T0 again, and that loads in the next instruction, skip if 0, and when it does that it increments the program counter, so the program counter will now be looking at 13 because it's only a single byte instruction. Now when the instruction happens, what it does is it takes the 0 flag and adds it to the program counter, but the 0 flag isn't a 1, it's a number 2, so it's either going to add a 0 or a 2 to the program counter. So on T-state 14 the program counter will be added to a 0 or a 2, so it will end up being 13 or 15. So if it wasn't 0, as in there's still 1 in there, the branch to loop will then does what that does is that says, the program counter will point to 13 here and do the branch to loop, which is this number, and it says there's the address it's got a branch to. So the branch command, well, that's got all the instruction modes as well, only uses the source one though. So it will set the program counter to 10. It will load this value here, to immediate value, which is what loop is, into the program counter. So the next time it runs, it will come back in at sub 1 again. So the second time we come round, we're doing the same again, but R1 only had 1 in it. So we're now subtracting 1 from 1. The program counter would have been looking at 12. 0, so we do instruction number 12, or the instruction at memory address number 12, which is skip if 0. That will then add the 0 flag to the program counter. In this case, the 0 flag is on. So your 13 now becomes a 15. So on your next instruction, instead of the program counter pointing at the branch for loop, it now points at the instruction afterwards. But it skips 2 bytes, these 2 bytes here, for the branch. So it's now gone to move, oh no, I'll just pick 33 into R1. Doesn't matter, whatever the next instruction is. And at the end of that, the program counter will be pointing at 17, because that is, oh, I've mistyped that. That 0 shouldn't be there. So, T0 and T1, same as they always are. 2 and 3 are not doing anything because we're doing, and 4 and 5 are not because we said it's R1. When we get to T6, we load in the B register again. We can take the program counter and put it into the B register. So program counter out into the B register. I think on the previous video I might have said A register, but it doesn't matter which. And then nothing happens on 8, 9, 10, 11. And then we get to T12, we're going to load the A register, and this is going to come from the 0 flag. So 0 output enable is going to go into the A register. So 0 flag out into the A register. Then T14, where the action happens again, we're going to add. So add our output with the add function. It's going to go into the program counter input, and C register is going to be cleared because we're not adding with a carry, we're just adding A and B together. So A and B get added together straight back into the program counter. So if the 0 flag was off, program counter gets 0 added to it, carries on. If it was 0 flag was on, it gets a 2 added to the program counter, so it skips 2 bytes in memory. So that's how the skip if 0 works. The skip if carry works is exactly the same, just uses the carry flag instead. Well, I think that's enough for this video. No actual electronics shown here, just how the system works. So don't forget to like and subscribe, and hopefully I'll see you in part 5.